Hello and welcome. In this Max tutorial, we will create a Shepard tone by implementing a multi-channel playback system in Gen. So before we start, maybe we should clarify what a Shepard tone is and how I am going to approach this. So a Shepard tone creates the illusion of a pitch that rises forever. It is created by laying multiple gliding tones on top of each other and then fading the volumes in and out at different times. So when the highest one fades out, a lower one fades in again. The main focus in this tutorial for me is not so much on the Shepard tone itself, but on how to create multi-channel audio in just a regular Gen patch without using any MC objects. So this is a very interesting concept that comes in handy in many different applications. For example, imagine if you want to do something like that in Rainbow where you don't have MC and then deploy it to a Raspberry Pi or something like that. So we will use a for loop where each iteration of the loop represents one channel of our multi-channel audio system, so to say. And each channel will then be one different gliding tone within this Shepard tone system. I know that it is way easier to create a Shepard tone just using MC objects, but yeah, that's not really the point of this video. So I think this video consists of two parts. So in the first one, we will just create one single sine sweep with an envelope. And then in the second part, we will create the for loop and turn this thing into a multi-channel system. I will start with an ECDAC and a live gain. Put this down here. Then I'll create a Gen codebox. I will turn down the volume here because we're going to test out a lot of things that won't sound that nice. It's just about looking at the signal itself. I think before we start the Gen coding, I will create the window for our envelope. So to do this, I will create a buffer, just call this one window, say Sam's 1000. So this is a buffer with a length of 1000 samples. Then we can use a waveform object to visualize this buffer. So just by saying load mass set and then the name of the buffer. Then I can double click this. Now we can see that of course the buffer is still empty. So at first we can fill it with ones. So just by giving it the message fill. And then we can say apply Hamming. No, that was wrong. So now we're applying this Hamming function on our buffer. I can also do a load bang. So this will be properly initialized. Okay. Now that we got that out of the way, the fun part can finally start. Okay, so what are we going to do now? We're going to create a sine sweep with this envelope. And to do that, so to read through this envelope and to also increase the pitch, I want to create a ramp that goes from 0 to 1 to kind of control both of our parameters. Normally we could just do something like out1 equals like the phasor object. And then let's use a live scope to look at the signal. So essentially this is what we want. But the problem is that when we're using a phasor inside of a for loop in Gen, it only creates one single phasor. So each iteration is referring to the same thing. But again, as I said, each iteration will represent its own channel, so it would need a different phaser, so we can't do it like that. So instead of doing this, we can just easily create our own ramp. And to do this, I will use the history object, call this one ramp. And this essentially means that we have some memory, because you can imagine if our sampling rate is something like 48 kilohertz, for every sample or for every frame in time, so 48,000 times a second, all of this code will be evaluated. And if we want to create a rising ramp and do something like ramp equals 1, and then say, okay, let's put the output here, and then say something like ramp plus equals 1, and then use a number box. Oh, sorry. You can see that the output is 2 because on every sample or on every frame, this gets reassigned. But we don't want to reassign it, we want to use the previous value, so we can use the history object, which gives us memory, and just say, okay, set this one to 0. Then I can delete this here. And now you can see that for every sample, we're adding 1 here. Okay. Where was I? Yeah, okay, so, but we don't want to add 1, we want to advance this ramp by a particular step. I think I will, just use a signal and assign this from the outside. So creating a signal object. Then we can use the translate object, because the input should be milliseconds and the output should be hertz. So this is pretty handy. And then I can just use an integer, and then we can see that 1000 milliseconds, so 1 second is 1 hertz, 2 seconds is 500 hertz, 5 seconds is, no, milliseconds, I'm sorry. Yeah, that's exactly right. I was confused for a moment. Okay. Then, let's call this input just our rate, so how fast the ramp is advancing. So I will create some comments so we know what is happening and where we are. So rate equals input 1. And then I also, so what I now want to know is how much I need to add on each sample so we get a ramp that goes from 0 to 1 in this specified input time. So to do this, I can say step equals our rate divided by the current sample rate. And this is exactly how much we need to add on each sample. So we get a ramp from 0 to 1 in the time that we specify here. So if I say step, of course this also blows up. So what we also need to do is we need to wrap this between 0 and 1. So we can say ramp equals the wrap function, ramp as an input, and then wrapping it between 0 and 1. So every time we go above 1, we'll start again at 0. And now you can, okay, 1 millisecond is maybe a bit short. You know what? I'm going to put in, because this was why I was confused earlier, I will multiply this by 1000, so the output will be seconds to hertz, not milliseconds. So 1 second, now we have a ramp that takes exactly 1 second. Now it takes 5 seconds, 2 seconds. Yeah, I think you should get the idea. Okay, then I think we can continue with creating the envelope. I will create a new variable, call this one envelope, and this envelope is created by reading through this buffer using this ramp. So we can use the peak object. Here we need to specify the buffer we want to read from. Then we specify the ramp between 0 and 1 we want to use. And because we're not using the actual like sample index, but a ramp between 0 and 1, we have to say that the index is phase. Now let's take a look at our envelope if this worked. No, it didn't. Oh, because I forgot to assign this or to declare this buffer in here. So I need to say buffer window. And if we're using the same name we used here, it should be working. Oh, now you can see that we're reading through this buffer at our specified rate. Okay. Then, yeah, moving on. Now I want to create the like actual signal. So first we need a frequency that's constant. Oh no, that's rising from like a minimum to a maximum and then starting over again. I would just call this section FQ. Yeah. First, I'm going to set parameters. I will call this one root node. So this is like the minimum, so the lowest node, and I will use MIDI nodes here. So root node is 36, and then I will also define like a range. Let's call this one node range. So we'll start with MIDI node 36, and then we'll have a range of 60 MIDI nodes. So the maximum will then be 36 plus 60, so 96. Then we can declare a variable called frequency. And now I want to use the ramp to go from the root node to the maximum, so from minimum frequency to maximum frequency. And so to do this, we can use the mix operator, which gives us a linear interpolation. So we're telling it what our minimum should be. And then our maximum is the root node plus the node range. And then again, we can use our ramp. So the ramp goes from 0 to 1, and 0 means this value and 1 means this value. So let's look at this for a moment. So I need the numbox again. Now you can see that we get the values between 36 and 96 as a maximum. And yeah, be careful with your volume here, because I guess this won't sound very pleasant. Okay, but these are MIDI nodes, and in the end we want frequencies, so we can use this function called M2F, so MIDI to frequency. And now we're getting frequencies instead of MIDI notes. Okay, so now this interpolation is done. But we now also need a frequency ramp because we're using a cycle object. And a cycle object is essentially like a sine wavetable. So again, we need a ramp that goes from 0 to 1 in the current frequency. So here we have the rate for our frequency ramp, and this will then drive the cycle object. So I will create another history object. Call this one FQ ramp. And then we can again apply this trick. So we can say FQ step. So the step for the frequency ramp equals the frequency we just got. And then we're dividing this again by the sample rate. No, like this. So this is our step, and then we can use the frequency ramp we got here and say this will advance, or we will add exactly this step on every sample or on every frame. And because this frequency is changing, the size of these steps will change. So I think we should also wrap this between 0 and 1. So this equals wrap itself between 0 and 1. Maybe we also want to take a look at this one. Yeah, I guess it's not that interesting. Okay, and now we can create the final signal. Let's just call this one signal. So we're using a cycle object. Oh no, sorry, that's not what I meant to do. So I'm creating a new variable, calling it signal. We're using a cycle object. So this essentially works like this peak object, but we already have like a sine wave table that's stored in here. So what we need now is to use our frequency ramp to drive this thing. And then again, I will borrow this from up here, say index equals phase. And now let's take a listen. Yeah, we have the sine sweep. Maybe we should slow it down a bit. But what I forgot is we also need to add our envelope. So multiplying this by the envelope, yeah, now you can also visually see that it's fading in and fading out. Okay, that was a lot. Moving on to the second part, making this thing multi-channel. So as I said, for the multi-channel adaptation, we're essentially doing the same thing, but surprise, surprise, multiple times. To do this, I will use, as I said before, a for loop, and each iteration represents then another or a single channel within our system. What we need to change first is, instead of using history objects, we need so-called data objects. So a data object is essentially a buffer, but it's just inside of Gen, so you can't access it from the outside. So instead of calling this one history ramp, we'll say this is a data object called ramps because we have multiple ramps, and then we tell it how many values we want to have. And this, of course, is then also the maximum number of channels that we can have, because yeah, each slot within our data object within our buffer represents one channel. Because the idea is we're always taking a value out of our buffer, computing the next value, and then putting it back in. This is why we need this kind of memory system. Same thing here for our frequency ramp. Of course, we need the same number of the same number of values or the same number of channels here. So now we can create the for loop. I will just put it here and then gradually copy and paste stuff in here. So maybe make this a bit explicit. Each iteration equals one channel. Okay, so then we can start for loop. Maybe, yeah, I will also create a parameter and call this one num voices, because we don't want to always use the 32 voices, so this would just be the maximum. So we can say num voices, I don't know, let's start with 16. And then I think we can say minimum is 1, max is 32. Does it work like that? Is that okay? So I'm not sure because, yeah, I'm all over the place with errors because I just reassigned this. But yeah, let's see. Maybe we have to rethink what we did here, but yeah. The current number of voices is 16. Let's leave it at that. Yeah, so moving on with the for loop, we're starting with 0. Then I is smaller than the current number of voices we're using, because we're going over all the voices. And then we're saying I plus equals 1 to go to the next step. And yeah, so we will iterate for each sample, as I said, 48,000 times a second. We will do this for loop and iterate over these 16 steps. Okay, then yeah, I think this one should more or less stay the same. It doesn't have to be reevaluated all the time, so we can just have it once here. It doesn't need to be done for every channel. So now continuing with the ramp. So we can't do this anymore because we first need to get the right value out of the buffer, then advance the ramp and then put it back. So to do this, we can say that ramp equals peak. So again, we're reading something. Oh no, that's the wrong kind of peak. Peak of ramps. So we're looking into this ramps buffer. And then we're looking at value I. So I represents the current channel. Then we're advancing this thing by one step, wrapping it between 0 and 1. And then after this, we have to put it back so that in the next iteration, we can get the already advanced value. So maybe to clarify this, we can say get value, compute next value, and then we're setting the value again. And to set the value, we can use the poke function. So it's just poke. Then again, which buffer or which data object we're using. We're using ramps. Then we have to say which value we want to poke in here. So the ramp value at which index or at which channel, which is again I. Then, yeah, I think the envelope can, this can stay the same because we have a different, so the ramp is different for each channel. So this can stay the same because it will just take the ramp of the channel we need. Then moving on to frequency, I will just copy this whole thing. Okay, what do we need to do for the frequency? Yeah, I think, this can stay the same because the ramp will be different for each of the channels. But this needs to change because now we don't only have one of these values, but we have one for each channel. So we can again say get value and say, frequency ramp equals peak of, just copy this, frequency ramps. So now we're looking into this buffer up here, or this, oh, spotted another mistake. This should be data instead of date. So yeah, referring to this buffer at this index or at this channel. Then we can again say compute next value. And of course we have to put it back then again. Set value is poking again. So we're poking, no, this one. So this is the data object we want to use. Then FQ ramp, this is the value we want to poke in at this index I, or at this channel. Then the signal equals cycle FQ ramp times envelope. Okay, this should more or less stay the same, but we need to change the output here because now we'll only ever get like the last signal or the last channel of the for loop. So what we need to do is we need to accumulate. So for every sample or for every frame, we accumulate all of the voices and sum them together. And then I will also divide this by the number of voices we have so this doesn't blow up. Okay, frequency ramps is not defined. Oh, yeah. Num voice is not defined. Yeah, because it needs an S here. Okay, this looks good. Now we can take a listen. Hopefully we hear something. Yeah, as you probably can hear, not much has changed because the problem is that each ramp starts at the same point of its journey. So we need to create some kind of an offset so that every ramp or every channel starts at a different point. So to create these offsets, where will I put this? I think I just put it here. Let's also put a comment here, set, yeah, rate offsets or something like that. And yeah, I don't want to set this all the time. I would just say if elapsed equals 0. So this variable, this built-in variable gives us the number of elapsed samples. So if you start the gen patcher, or if you reload it, this will be 0, or if you change anything in here, this will be 0. So we want to set these offsets only if we're starting. And I think also when we're changing the number of voices, because then we have to reset the thing. So either we're doing it when we're starting or when the number of voices changes. So to do this, we can say like the delta. So this gives us the frame or sample by sample, the difference of a value. So num voices. So if this changes and this is like the change is bigger than 0, we also want something to happen here. Oh no, not like that. Oh, but I forgot something, because here it could also be smaller than 0, because imagine like when we're changing the number of voices from 16 to 17, this will be bigger than 0, but if we're changing it from 17 to 16, again, this will be smaller. So I want to take the absolute change. This should work now. Okay. Then, yeah, we need a for loop again, iterating over all of our voices. And this time I want an offset between 0 and 1 that's different for each of our ramps. So to do this, we can say offset equals I, so the current channel number, by all of our channels. So for channel 1, this will be, or for channel 0, this will be 0. For channel 1, this will be 1/16th, I think. Yeah. For channel 16, this will be 16 divided by 16, so 1. So we get a different offset for all of our channels. And then we have to set those values. So again, we can say poke ramps at index. No, first I have to say the value that I want to poke in, and then I set the index. So now every time we're restarting the gen patcher or the number of voices changes, this will be, we will set a new offset. Okay. If I didn't make any mistakes, this should work now. Okay, let's listen. Yeah. That's essentially what I wanted. We can also divide our rate by the number of voices. And increase this a bit. Yeah, now you can hear this auditory illusion of this ever-increasing pitch. And yeah, here we can change the number of voices. Of course, it sounds different when we're just using 8 or if we're using 32. And yeah, you can play around with the number of voices. It also makes a difference what kind of offset you're using and what kind of note ranges you're using. So yeah, try out different parameters and see what sounds best to you. What we could also do, so maybe we can take a look at what we just built using the, where do we have it? Using this patcher here, so we can see the spectrum. So now you can see these are all of the peaks, and the higher they get, the lower the volume. Maybe let's make this a bit faster. Now you can see that all of the peaks are rising in pitch and decreasing in volume, which is exactly what we want. Yeah, I think we're almost finished here. What we also could do is set a direction. So now it's rising all the time, but we could also create a parameter, call this one direction. And depending on this parameter, we can say that it's rising or falling. And where do I need to put this? I think somewhere here, because we need to change the frequency ramp. So this one needs to change. So maybe we can reassign this and say something like ramp equals direction. So when this one is true, we just want our ramp, and if this one, so we're direction, no, it's correct. So what this means is, okay, we're evaluating this direction. If this one is true, so if this one is 1, we just want to have our ramp, and if this one is false or 0, we want to have 1 minus the ramp, so the ramp will, or the frequency will be decreasing. Let's listen again. Yeah. Where do we have the direction? Here. Yeah, now it's decreasing and now it's increasing. Yeah. You can, as I said, you can experiment with different kinds of offsets, with a different range between minimum and maximum, with a different number of voices, and also with different windows. So I really like this window function. I think this sounds very convincing to me, but yeah, do your own experiments and see what sounds best to you. Yeah, I think that's it for this video. I hope you found this useful. Thank you for watching.